let's look at another strong nucleophile reaction, which is the Wittig reaction. In order to do a Wittig reaction, you need the Vitic reagent. And so I'll just draw one here. You have a carbon, which is going to be the more nucleophilic thing. And that's going to be bound to a phosphorus that has 3 benzene rings on it, or phenyl groups. This carbon right here is going to be quite nucleophilic. So I'm going to draw this in the charge separated structure here, resonance structure. And here is the general structure of the Wittig reagent. And the carbon part is actually what's going to do the attacking and all of that. It's in an equilibrium with the phosphorus with a double bond to the carbon. But the equilibrium lies more in this direction. Now I'm just going to abbreviate each of these phenyl rings by just pH. So we've got this carbon nucleophile. Now it does a really neat reaction. It replaces oxygen in ketones and aldehydes with the carbon. So let me just draw one of these reactions here. So we'll do one with an aldehyde, and we'll add our Wittig reagent, which in this case is going to have an ethyl group on it. And here's our reagent, and we'll need to do this in a like an ether solvent or something similar to that. So we'll just say THF. And the result of this reaction is, and I'm going to draw it this way just so we can kind of identify what we've done here is we've replaced this oxygen with that carbon right there. And when we do that, it leaves a double bond. Now, we'll get this reagent, or this product, and we'll also get the other isomer. So this reaction will, if there's a possibility of an E and Z isomer, if they're different, it's going to make both. It doesn't necessarily make them both in the same amounts, but it will make both of them. And for now, we'll just say that if we want one of these, we'll have to deal with a lower yield by the fact that it will make the other one as well. And maybe we're going to do an addition reaction to this, and possibly the E and Z doesn't matter in that case, but just know that we'll get both E and Z. This reaction also works with ketones, as I mentioned. So I've drawn it with an aldehyde, but if we had a ketone, we would just have some, carbon stuff over here rather than the hydrogen. So let's go over the mechanism now for this reaction. So we're going to have, draw it over here. So here's our Vitic reagent. And we'll have that attack. This is going to go up there. So pretty standard so far. Carbon nucleophile attacks the carbon here. Electrons move up to the oxygen. But we're going to have something different because that oxygen is going to leave as part of the process. As you can see, there's no oxygen over here in the products. So we get an intermediate here. Oxygen has the negative charge on it up here. We've got our new carbon bond. Like that, and I suppose we still have the hydrogen here from this hydrogen right there. And we're going to have our phosphorus still bound to the carbon that's part of this carbon right here, right? Next, we're going to have the oxygen attached to the phosphorus. There's a plus charge on the phosphorus. I'm going to draw that in. Should have drawn that in over here too. So this negative charge is obviously attracted to the positive charge on the phosphorus. So we get an attraction there. And this makes a butane. Because it's got this two positive and negative charges separated on each other. That's going to have that attack, and it's called this. And I think I said that wrong. Betaine, I believe is the way they say it. And it looks like betaine, but I've seen that it's supposed to be B and then taine. But anyway. So now we're going to have this little squared up oxaphosphatine right here. Still got the hydrogen there. Next, we're going to do a little bit of square dancing here and have things move around a little bit. And then I'll just draw one of the isomers that this can make, because this could be rotated around in different ways when it does this approach. So we could make that isomer, and of course then it also makes the other species with the phosphorus. Still got the phenyl groups on it. Now, one of the driving forces for this reaction is this phosphorus oxygen bond. It's pretty strong, and of course in some cases you might even draw this with a double bond here and not have the charges separated, and that's fine to do because phosphorus can have an expanded octet. But again, oxygen really likes to bond with phosphorus, or phosphorus likes to bond with oxygen, I should say that direction. And because this is quite a strong bond, it will tend to drive the reaction forward. So this is an important reaction because it allows us to control where we're putting a double bond. In other cases, especially if we're in a long chain or just an internal chain and we wanted to do, say, an elimination reaction, we wouldn't necessarily have control over where that double bond goes. Whereas in this case, we can control which carbons it ends up between. And that can be quite an advantage. And even though we're making both the E and Z isomers, putting that double bond where we actually want it can be quite helpful, especially when other reactions, like an elimination reaction, can suffer from lack of control between E and Z isomers, as well as lack of regional control. Whereas, we might have a double bond end up on a different carbon than we initially wanted, making a different molecule, then we're just reducing our yields. So this is quite an important reaction. And in the next video, I'll talk about how to generate the Wittig reagent